Hi everybody, we're back. We're back for our new webinar series. It's now it's night for us now. Our clocks have gone back, and I think yours have too over in America. So good lunchtime, happy lunchtime for you guys, and on the West Coast, happy morning for you if you're joining us from there. My name is Catherine Smale. I'm Ecclesfield Callahan's BD and marketing manager. And so today we're going to be having a presentation from Angie Neefus, who joins us from our New York office. Angie is going to give us a presentation in the vibrations of structures, which is going to be very interesting. I've just had a sneak peek and it's all sounds very good. Just a couple of things first, just to kind of go through things. There's a little chat box to your side screen on the right hand side of your screen. Say hello, feel free to say where you're from. That would be really good to find out who's there and watching us. There are questions, so you can ask questions in the little chat function at the side. There's a great function whereby you can kind of give it a thumbs up if you like it. So, and that kind of promotes the question up to the top, which will be good. And all that's left for me to do is to introduce Angie. So Angie is an associate in our New York office, as I said, and she started out as being a structural engineer, but now does structural engineering and also has turns her hand to all sorts of different types of engineering that is keeping going on. So anything from working for the contractor to facade design to specialist structures. So I shall hand over to Angie now for the good and bad vibrations in structures. Prize goes to anybody who can name the song that might have been taken from. But I'll hand over now. Thanks.
Yeah, so just imagine the Beach Boys are playing in the background. But hi, everybody. I'm Angie. So today we're going to be talking about vibrations and structures. I guess a little bit of a preface for this presentation is vibrational analysis is a very broad topic. So this, and we really don't have enough time. We could spend days talking about vibrational analysis. So I think this is, really meant to be sort of a primer to kind of get you started thinking about what's involved in vibrational analysis and the different things you have to sort of consider. And so with that in mind, we're going to start with the very basics. What is vibrational analysis? And in the sort of most generic terms, it is just the study of a structure's dynamic response to a forcing function. And these can be forcing functions caused by people, by wind, even blast engineering is kind of a form of vibrational analysis. This presentation, we're really going to focus mostly on a footfall analysis, particularly with regards to stairs. But as I say, this is a very broad topic that encompasses a lot of things. So people interact with structures in all sorts of ways. I've sort of tried to include some of the ideas. This could affect gyms, even dance halls, dance studios, laboratories with sensitive equipment that need to limit the vibrations, or in the thing we'll be focusing on mostly today is people walking downstairs, things like that. So I think I tried to sort of break this down in a way that there's kind of three main components that you need to consider when you're sort of approaching the vibrational analysis of a structure. And the first thing is, what is the force function that you're going to apply, right? So for, walking, like how do you approximate, the force from a person walking on a structure? There's everybody walks differently. There's a million, these are 4 different examples of 4 different people walking, right? There's a million different ways, it varies from person to person. And so you really just have to sort of, find something that's reasonable and sort of statistically representative, while just sort of understanding your probability of exceedance and things like that. So you have to worry about the force that you will need to consider. You have to understand the inherent dynamic properties of the structure. So that's going to involve typically some kind of modal analysis to figure out the natural frequencies of your structure, as well as the modal mass. And then the third component is what is the structure's response to the forcing function, and that's going to be sort of a function of both the force applied and the dynamic properties of the structure, right? And so we'll use, that, and we'll get into sort of how you do that, but we'll use that information to determine, what is an acceptable performance criteria for our given structure. Another important question I think is why should we care? Like a good example that I can give you. Let me see if I can do this transition. This will be familiar to everyone. So
what you're going to see now is a clip of the
we all know the Millennium Bridge in London.
In 2000, you'll see the results.
And when it first opened, this was a bridge, very high profile. Lots of studies were done, but it ended up being the case that once the public started to interact with the structure, right, it had this sort of unanticipated behavior where it was very, very wobbly. And this is a very extreme example of it was a perfect storm of it just hit the resonant. It just hit the natural frequency just right of the bridge, and it just created resonance. And you can see how all the people are sort of walking in time and making everything worse. So that was a really interesting example. But yeah, so sorry, let me switch back to my. So as we moving forward, structures are getting lighter. They're getting longer spans, thinner. Everything is just pushing the boundaries of what's possible. These are some Apple projects we've worked on. Even like the sky pool. Things are continuing to push the boundaries of what's possible. And so as we sort of reach those extremes, we really have to have a good understanding of how that structure is going to behave once people are interacting with it, because it used to be the case that in the 30s the buildings were very robust, and it didn't really it wasn't really going to be a problem. But now things are much thinner, so we really need to understand that interaction a bit better. So now we're going to get a little bit into how we can kind of quantify the vibrational performance of a structure. And the short answer is it really depends. It depends on sort of several things, but kind of going back to those three main umbrellas of the components of vibrational analysis. When you're considering the force function that's going to be applied, it depends on sort of what you're analyzing, as well as the behavior you want to observe, right? So for the case of a stair, a walking forcing function on a flat surface looks different than ascending or descending a set of stairs. So you need to kind of sort of consider all those different components when you're looking at the vibrational performance of a stair. There is also sort of ranges of what is possible. Both the AISC Design Guide 11, which is the American Institute of Steel Construction, as well as the CCIP, which is the Cement and Concrete Institute publication out in the UK. They this sort of gives you a good idea of, it's really, there's a very large range of the frequencies that are possible. And so what you have to do is kind of consider, rather than just one potential walking frequency, you have to consider a whole range of frequencies, right? AISC gives some ranges depending on whether you're walking or running or going downstairs. And then in addition, there is the added component of considering not only the first harmonic response to a stair, to a forcing function on a stair, but there's also the second and third and sometimes fourth harmonic response that you need to consider. And that just sort of, all it's doing is adding to the quantity of cases that you need to consider, right? So what we're talking about is this is not something that's going to be done by hand. This is something that you're going to sort of run a bunch of iterations to sort of get your results. And then the second component of the dynamic properties of the structure, depending on the kind of structure you're analyzing. If it's a simple beam and girder floor system, you can determine the natural frequency with an equation based on the deflection. Whereas if you have a much more complicated structure, you need to do a finite element analysis to determine the natural frequencies. This is on the right, a snapshot of a stair that we've worked on in the past that will be a case study. So we'll go on into that in much more depth, but this was done in strand 7. But any finite element analysis will give you multiple results that you can use. And then the final component of what is the structural response to your forcing function, right? So that's kind of the biggest component that will actually give you the vibrational performance that you can then use to determine to see if it's acceptable. This is a flow chart from, again, that CCIP 16, which is a really great document that I recommend everybody check out if you want to understand vibrational analysis better. But basically, if you're above 15 hertz, then you're considered sort of out of the range of being able to be, of the structure being able to be excited by footfall. Whereas if you're under 15 hertz for your frequencies, then you need to really do a much more in-depth analysis. Pretty much every structure built in the last 20 years has a frequency of under 15 hertz. That's very robust. So, and when that's the case, basically what happens is, this is another flow chart, very in depth, but what it boils down to is you have to look at each walking frequency you want to consider, which is generally a range. You have to look at each harmonic of that walking frequency, and then you also need to consider that at each structural mode that your structure experiences, and that will give you basically a graph of response factor, and that's used to calculate your peak acceleration, which we'll get into in a bit in our case study. So then there's the question of, okay, we've gone through all these steps. We've figured out what the vibrational performance is of our structure. How do we know that that's acceptable? And the short answer, again, is it really depends. So basically, vibrational performance is really all about what a human being is able to perceive, right? Because this isn't really an issue of safety. This is really an issue of comfort. And different settings allow for different vibrational frequencies to be able to, vibrational accelerations to be able to be felt. And so, the way AISC approaches it is, there's different acceptable peak accelerations depending on if you're sitting in an office, right, where you're stationary generally, so you'll be able to feel some, but you're not sleeping, right? So there's offices versus residences versus when you're walking on a pedestrian bridge, you're going to be comfortable with a larger amount of vibration than you would be if you were sitting at your desk or sleeping. And to that end, similarly for stairs in particular, you're going to have a different level of comfort whether you are walking down the stairs, running down the stairs, or if there is a large group running down the stairs for an evacuation event or something of that nature. You're going to be okay with different levels of perceived vibration, right? And then, this is a similar, so this is the British standard 6472, which one of the main differences between the US codes and the UK codes is the US codes work in peak acceleration, whereas the UK codes work in RMS, root mean square acceleration. Since it's all about a perception and a threshold of perception, it doesn't really make a difference. They're more or less the same concept. As long as you're consistent through your calculations, you can use either. But they similarly break it down by environment, right? So resonance during the day versus at night versus, if you're working in a workshop, you sort of expect a certain amount of movement. Critical working areas would include things like labs with sensitive vibration, like vibration sensitive equipment and things like that. Right, so that's sort of a general, these are the things you need to think about. And then I wanted to go into a bit more depth of a case study that we did. And this is the MoMA expansion here in New York. We did the final engineering for the blade stair in conjunction. We worked for the metal fabricator Dante TC in Argentina. And this is a very interesting project because it's one of these things that, I went there, shortly after the expansion opened in October of 2019. And you don't really notice when you're using the stair that it is this really complex structure, but it is actually very involved and required a lot of analysis from the vibrational perspective. So it's really very interesting. So this is some drawings. So basically, the way this structure works is, believe it or not, it is actually hung. You can sort of tell at the bottom, but this sort of central blade, as it's called, does not extend all the way to the ground. And so, the stair is sort of cantilevering off of this central blade, which is then hung from the structure above. And it is comprised of a series of HSS tubes that are then clad, so you don't see those in the end. And then basically the treads sort of cantilever off of the central HSS tubes. They connect at the landings, obviously, with the stair. And then the sort of return landings are these kind of monocog, stiffened plate, tapered sections. And the reason for this is, the preliminary design that was done by the engineer had sort of, in an effort to get the vibrations under control, they had large amounts of steel on these landings, which when they got to us to do the final engineering for, we were struggling to get those to work as originally anticipated, and it turned out that a big reason for that was the landing structure was very heavy, and so we thought, what can we do to make this work? And it actually ended up being the case that taking steel out and making the structure lighter while still maintaining as much stiffness as possible ended up allowing us to get that structure to work, which was really pretty. It's pretty impressive. You don't notice that it's even cantilevering when you're on it. So this was analyzed in strand 7. That's what we tend to use for a lot of our projects. And basically what we had to do was take the structure and find all of the sort of primary modes of it ended up being the case that the lateral movement of the landings were sort of the first 3 primary lowest modes, and then it was sort of the vertical deformation of the landings. And so, for each of these modes, we then had to, you know, pick a point where we think and we obviously had to try several to sort of get the worst case, pick a point of where we think the forcing function would have the largest impact on the structure. And then we would go in and analyze that mode. So there's one of these frequency response factor graphs for each of the modes based on the different walking frequencies we assumed. And then those are used to determine the peak acceleration with lots of equations that are not worth getting into at this moment, but we can definitely talk about them offline if you'd like. But we basically use those to calculate the peak acceleration and then compare that to what's the guidance of allowable or acceptable acceleration is for each of the different cases. One thing that's worth noting is the rapid descent of a group almost always doesn't work. But the thought process is, you know, if you have, you know, a large group of people evacuating for some reason and the stair ends up being a bit bouncy, we think people, you know, the idea was people wouldn't really mind necessarily in that case. And, you know, vibrations are something that it's not a code requirement, right? It's really all about what ultimately the owner is willing to accept, right? And so these are just discussions that need to be had. You say, you know, we've done this analysis under most 90% of the use cases, it's going to be fine. If you have a large amount of people going down the stairs, it might get a little bouncy. Are you okay with that? And so that's sort of the one of the things that it almost never works. But yeah, I'm trying to think if there's anything else I had to say about this one. I think that might be it for me. I've included a reference slide, which you guys can sort of look at towards the end, or maybe in the recording or something. The CCIP 16 is a really good reference in terms of sort of understanding the process involved in vibrational analysis. I highly recommend that. And then, you know, again, this is something that it's not codified as well, particularly in the US. It's more of these are the guidelines, and you have to sort of piece out sort of what you can get the owner to sign off on. Yeah, so that's all I had.
Oh, perfect timing, Angie. Absolutely perfect timing. No, really super interesting presentation, and it's kind of vibrational analysis, obviously super important. And I actually remember, so I started out as a grad at Arup, and one of my friends was a pre-uni when the Millennium Bridge problems hit, and it was quite fun because apparently they had to, at that point in time, they shut the bridge down, obviously, because they were a bit of a hoo-ha. Nobody really wanted it to be so wobbly. Yeah. And they basically gathered a whole group of them together from Arup. And the dead of night, they went down and they got commemorative baseball caps. They all wore baseball caps, and they were all kind of marching backwards and forwards, kind of trying to test out the vibration on the bridge. I mean, that's quite a special moment as an engineer in terms of sort of, you know, getting to test something like that out, and without the fear of it falling down, you know, kind of
exactly. Yeah,
it's saying it's kind of, you know, it's kind of SLS rather than the ULS, and so
yeah, exactly. And it's one of those things that, you know, you can do all the analysis in the world, and you know, you still have to kind of see what happens when it's actually built. So that's really,
there's been lots of documented things about the Millennium Bridge and about
horizontal
rather than the vertical and what have you. But do you now sort of are you now very aware of that in terms of designing for the horizontal and things like that, and the horizontal vibration as well as the vertical, and in those situations?
I mean, I think the Millennium Bridge really brought that to light in a lot of ways, and there have since been dozens and dozens and dozens of papers.
Absolutely.
One thing that's kind of interesting is it's still not really covered very well in the sort of American codes. Well, certainly not in the codes, but even in the American sort of documentation. The AISC design guide just sort of has this general threshold of you should have at least a frequency of 2.5 hertz laterally to not excite any issues. But that's, while that's probably covers sort of the first harmonic, there's this issue of footfall analysis in particular that you have, the second and third and sometimes fourth harmonics to consider. And so I think, we're still sort of working on incorporating that sort of more explicitly. But it's definitely a real thing, and particularly on a thing like the MoMA blade stair where you have a switchback, you really have to be careful of when people are turning around. That lateral force is a lot more of an issue than a straight run stair.
Absolutely. Do you sort of in the case of where it's sort of, I suppose the codes in America fall short, do you look for kind of other codes to kind of back that up? Do you sort of
I mean, I would say I actually use the UK codes a lot more for things like vibration. They just have a lot more documentation on sort of like a established process that I find very useful and very sort of thought out. So that's definitely look outside the US for things like that.
It's and on that, actually, on the references slide, we will be putting that up when we put this back up on the website, because we'll put the presentation up on the website for everybody to see, but we'll put those references underneath to make sure that kind of everybody can see which ones those ones are, because it's really super useful. I suppose that kind of ties in terms of the movement you were talking about before, that Olivia had a question. So when do these vibrations and / accelerations go from emotional to being structurally critical?
I would say for footfall, like induced vibrations, I would say they never become structurally critical. The Millennium Bridge is interesting, right? Because structurally it was okay, but it just made people really uncomfortable. So it's really hard to say, because it just depends. I mean, it really is like a feeling thing and a perception and what people are okay with. And that was,
you were talking about earlier about the fact that it's more of a perception thing.
And so like, the Millennium Bridge sees thousands of people a day. So they had, that same exact bridge in a much less trafficked area. It may have never really become an issue. So it's hard to say until it's actually used.
Yeah, and it's funny, I suppose, because the layperson kind of wouldn't necessarily know that movement isn't critical.
Right.
You don't necessarily know that, and you kind of just anything swaying might kind of be perceived as being, oh, it's going to fail on me or something like that. So
right.
Especially if it's getting worse when more people are on it. So
yeah, but it's like rope bridges that have been around for thousands of years. They'll sway all over the place, and they're not going anywhere.
I remember going in, and we had one rather fun day of kind of testing out lots of different stairs. So we basically just walked around London trying to find different staircases, and then kind of estimating what the frequency of the staircase might be depending on its response of how hard we stamped on them.
Nice.
That was quite a fun day to do.
I admit, every time I go down a sort of interesting stair, I tend to jump on one of the landings and see how it's doing.
It's quite good fun, isn't it? Just to test it out, have the engineers quite got it right in that sense. I know that feeling. So Dazanian, I'm very sorry if I've pronounced that incorrectly, but so on the MoMA case study, how is the lateral movement reduced to minimum? Is it only with the middle blade construction, or is it connected sideways to the substructure / shell?
Yeah, so it is primarily actually dealt with through the blade itself. There are landings at each floor that have some lateral stability in them, and so I think those actually do play a decent role. But it is just the blade itself, and then the landings connecting to the stair, and that's it. There's you can sort of see it here. This is from the outside, which is where it's the most impressive, I think. There's nothing on the sides. It's all just a blade and then the landings.
Yeah, that is.
It's really cool.
It is really cool, and I wouldn't. But
You
you're right,
can't
I wouldn't have
tell.
noticed it was cantilevering until you
You
look.
can't tell from the inside. It's
Right.
a bit of a shame.
But the underside on that left picture, you can kind of sort of get an idea of the fact that it's
Yeah.
kind of
Yeah, it's just
slightly
it just
more magic
stops.
than first might appear. So Hubert asked, kind of for the MoMA stair, did this glass stair rail attachment configuration contribute to its overall vibrational performance, positively or negatively?
I would say it didn't help. It was definitely, the thing that's not shown in this is, the glass handrail is also sort of considered in our full building model, or full stair model. But it didn't help, but it was not severely detrimental, no. It's just a consideration that we have to take.
Is that because it's acting as some kind of restraint to the edge of the stair?
Yes, I mean there are situations where we've actually relied on the glass handrail to sort of get certain stair configurations to work. In this case, there was enough robustness in the blade itself that it wasn't necessary.
Yeah.
But yeah, no, it definitely, and sometimes, it could be the case that it's actually the handrail that we've used. When needs must.
I suppose we are known for our glass design in terms
yes.
of structural materials, so therefore it's kind of there are ways and means of doing these things, aren't there, in terms of that. So back to the MoMA stairs. Eddie has another question on this one. If the stairs are suspended from the structure above, what is preventing the stairs from swaying side to side? Is there no connection from the stairs to the ground?
There are no connections to the ground. I mean, it's just the landing connections at the intermediary floors, and then the hanging at the top.
So it does have a restraint kind of at the floor level.
It has, right. So like it has a restraint here, right, to this is like looking at one of these floors. There is a restraint, sort of at these landings that's sort of providing a little bit of lateral restraint.
Yeah.
Yeah. And this is the hanger at the top. It's not a pure hanger. It does have some amount of resistance. So it is hung, but it does have some amount of rigidity
but it's
at the top.
Push-pull kind of stop.
A little bit, yeah.
Okay. Yeah. And what kind of supports were considered at the full landings to the main slab? I think you've probably just sort of answered that one, I suppose. In terms of...
I don't actually have the landing details in here, but yeah, they're mostly just pins, but they are providing some restraint.
Yeah.
And restraint laterally as well in both directions.
Oh, so Wayuk Lau has got a question on slightly different now, kind of moving off the stairs. Should I quantify the structure in terms of response factor or natural frequency or vibration dose value?
So yes, I did not really get into vibrational dose values. I mean, the difference is the vibrational dose values sort of, as opposed to a frequency, is kind of like an immediate response of the structure, whereas the vibrational dose value is a sort of averaged over a length of time. So it really depends on, I guess, what you're looking at. I think sorry, I'm just looking at one thing. I think in the British Standard, it talks more about for residential comfort. It talks more about vibrational dose value because it's over a period of time. But again, it really depends on what you're looking at.
Yeah, and I suppose in terms of sort of the different types of structures, they all have different sort of criteria, don't they, around kind of whether or not you're talking about offices or residential or staircases or different elements within those buildings and things. So you can have a different a different value for that in terms of what you're doing. What's the most unusual kind of application that you've kind of worked on for doing this kind of thing?
We've had some facades with sort of these fins that extend out past the glass line, and those had some sort of vibrations induced by wind. That was a pretty interesting one to try and understand that and minimize that vibration, because that was really a case of, you just don't really want to see these things fluttering around. It was more of a visual concern. That was kind of interesting. And then I've had to do a blast analysis on an all glass facade, which was actually pretty cool. Which is kind of, it's the same sort of process as, footfall analysis, just with much larger loads. And that does have that starts to have a level of safety involved, but that was probably one of the coolest things.
How do you model kind of doing a blast analysis in terms of the vibration?
Well, it's more of just like you have a force, you sort of figure out what your loading function is over time, and then you just apply that to a finite element analysis of your glass, and that was a glass fin system, and you just sort of see what happens.
It does sound exciting, doesn't it, in terms of how you apply those loads? I suppose it's more of an impulse load that you can kind of apply to something. But yeah, no, because you guys do blast analysis over in the New York office, which is really cool. Because I know that one of our projects has been the glass box in the Washington Museum. I want to say Washington Museum. I think I've got the project name wrong.
Under the Gateway Arch in St. Louis?
No, it wasn't that.
No?
I will think of it, but
that's also blast designed.
Oh, that is blast designed. Yes, that one.
Yeah, no, that's a really cool project, actually.
Yeah, I bet. But it's kind of what materials, kind of in terms of the materials, can you apply the vibrational analysis to? Are there kind of any that are more susceptible than others?
Concrete's actually an interesting one, because it's so heavy. It can actually sometimes be susceptible to vibrational issues, but it's not something you really think of. But you really can do it on anything, even wood.
Yeah. I suppose it's kind of counterintuitive to add more mass kind of might make it worse.
Mm-hmm. Yeah, exactly.
Structure might be actually is actually probably better for it.
Mm-hmm.
I think that is something just counterintuitive. But yes, so Byron Harrison asks, what are your recommendations or analysis procedures for dealing with rhythmic forcing, such as dance? As acousticians, we generally aim for stiffness and higher natural frequency to resist motion, but admittedly neglect considerations of overall mass and damping.
I think that's a fair approach. I think, you need the high, the higher you that's where sort of that 15 hertz. It's a very high it's a really high goal. But that, the higher the frequency, the less potential issues there are to be had. But I guess, sorry, I forgot the first part of the question.
So recommendations for dealing with rhythmic forcing, such as dance.
Right. So, I think it's dance is actually an interesting one, because you can actually put in sort of like a impulse, actual forcing function, rather than just considering different frequencies. And I think maximizing stiffness, minimizing mass is generally sort of where you want to go. Higher the frequency, the better.
Yeah, just to make sure that you don't kind of start to excite it. Make sure it's thoroughly over that threshold.
Yeah.
And I think we've probably got time for. One more question. Should we take one more question? Okay, so Lucas has got. Do you think that a landing can be considered to have different, narrower frequency range compared to steps, using a walking frequency range similar to that of the floor? People are not really ascending, descending, but rather walking on a flat surface, one might say.
Agreed. Yeah. I think you have to on a stairs, particularly with switchback landings like this, the frequencies you're considering on the landing itself would be closer to walking rather than ascending or descending stairs. But the interesting thing that you have to consider is the response on the landing of somebody walking up or down the stairs. You know, that could potentially be the controlling thing. So you need to sort of consider somebody walking on the stair, how that's perceived on the landing, as well as walking on the landing, how that's perceived by the landing.
It's more of a sort of a pattern loading, isn't it?
Yeah.
Sort of one's impact on the other,
Yeah.
rather than necessarily in isolation on its own.
Yeah.
Yeah. Well, I suppose that's a good point, and kind of where to wrap things up. I'll let you go back to the interesting times that are going on in the US at the moment. We're not going to mention anything about it, but
Nope.
I just hear there's some interesting things going on at the moment.
Yeah.
So maybe
It's
I'll
exciting
go
time.
back to your day and kind of working out what's going on for that one. But in terms of saying thank you very much indeed for joining us, those in the US, have a lovely kind of day and afternoon, and don't forget to tune in for next week's presentation. It's going to be very interesting. It's going to be a different format. We're not going to have a presentation. We're going to have more of a sort of fireside chat, and Angie is going to kind of speak quite candidly about what it's like to set up a new office and what it's like to set up a new office in Hong Kong. And so I think there are going to be some really interesting things that come out of that, and just dispelling some myths and kind of looking at where the different markets are opening up, what's been successful, what hasn't been successful, kind of all the different hints and tips. And he's got some hot tips to kind of to impart for that one. So sign up for that. If you go to our website, the news section of our website, you can sign up there. And alternatively, we'll send around also an email as well on Monday. So join us next week, and also look up the rest of the ones that we've got there. And I hope you have a nest of a good day. Super. Lovely to see you guys again. And we'll speak soon. Thank you very much. Bye.